Hey everybody, this is going to be the first recording. This is a recap of Tuesday, September 1st lesson. So let me set up my tablet here and get started. All right. So, one moment, please. All right, everyone. This topic is going to be basic chemistry. Yeah, that is an ugly font. Oops, let's go back. Draw. All right, this should be better. Okay. Here we go. So the first unit of this course is biochemistry. And in order to understand some of the biochemistry that we'll be doing, you need to understand some of the basic chemistry. And that is what we will be going over. So let's begin. This is going to first cover atoms. Atoms are the smallest unit of matter. If you look at the periodic table, you have all the elements that we know exist. There's about 118 of them. 1 through 92 are mostly naturally occurring. And then after that, you have a lot of synthetic ones, which are man-made, created in labs and whatnot. So in an atom, you have 3 subatomic particles. You have protons, which have a positive charge, and neutrons, which have no charge at all. So we indicate them with a 0 for none. And they reside in the nucleus. The nucleus makes up like 1% of the atom's space, but it takes up 99% of its density. And then you have electrons, which have a negative charge. They orbit the nucleus in energy shells, or energy levels. And every energy level has electrons on it. The first energy level has 2 electrons. The second energy level will have 8. Then the third will have 8. The fourth will have 8. And you just keep going. We're not going to have to get into all that. Of these subatomic particles, the electrons were discovered first. And when they were discovered, the discoverer did not know that they had a negative charge. He just knew that they had an electric charge. So he named them electrons. I imagine if he knew that they were negatively charged, he may have called them negatrons. And then protons came after that, and then neutrons shortly after that. So these are the 3 subatomic particles. Protons and neutrons are about the same size. They're weighed in atomic mass units. A proton and a neutron are about 1 atomic mass unit each, while an electron is about 0.0005 AMU. So they're very, very small, but they counterbalance the positively charged protons. All right. Now, some of the elements that we'll talk about, we're only really going to discuss like a maximum of 10 elements this entire school year. And there are 6 big ones. I'll get to them in a moment. Actually, I'll get to them right now. The 6 elements that generally compose life are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. It's SCHNOPS for short. Carbon is the big one. All life on this planet is carbon-based. Hydrogen is the most abundant element in the universe. It's the smallest, it's the easiest to bond. Nitrogen is one of the foundational elements of proteins, and proteins were the first macromolecules on Earth. Obviously, we need oxygen to breathe. And then you have phosphorus in your DNA and sulfur in some proteins. These four are the big four, with these two to a lesser degree. But these six together make about 96% of life. So 96% of you, me, your dog, a tree, they're pretty much going to be carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Okay, and as I said earlier, elements 1 through 92 roughly are naturally occurring. You have metals, you have nonmetals, you have metalloids. All six of those are nonmetals. And then you have isotopes, which are atoms of the same element with differing number of neutrons. And when I was in school, I never understood what that meant. So I'm going to break it down for you. One of the most popular isotopes that we have out there, carbon-12 versus carbon-14. Now, if you look at a periodic table, carbon has an atomic number of 6, and it has a mass number of about 12. So within the nucleus of a carbon atom, you have about 6 protons. That's the atomic number. You have 6 neutrons. The atomic mass number is protons plus neutrons. So 6 plus 6 is 12. Now, because carbon has 6 protons, it has 6 electrons. So here's the first energy level. And on the first energy level, you're only allowed to have a maximum of 2 electrons. Now, carbon has a total of 6. So 2 will go on the first level, and then the other 4 will go on the second level. So this is what carbon-12 looks like. Carbon-14 is going to have 6 protons and 8 neutrons. 6 plus 8 is 14. The proton number doesn't change. The neutron number can change. And then when it comes to isotopes, the electron number doesn't change, only the neutrons. Carbon-14 is radioactive. We use it for carbon dating to determine the age of ancient organisms or artifacts. It could be King Tut's tomb, it could be a pyramid, it could be a Tyrannosaurus Rex. You often hear a lot about carbon dating in media. You know, there's movies like Captain America Civil War or Prometheus or Transformers where they mention carbon dating a lot to determine the age of older remains or discoveries found. And when we die, carbon-14 begins to decay. So scientists can calculate how much is left when, like, the body of an individual is remaining, or excuse me, how much is left versus how much they should have. And that's all done through half-lives and radiometric dating, which you should have learned in chemistry. If you haven't learned any chemistry, you will soon, once you do take chem. Now, all those organic elements, the carbon, the hydrogen, the nitrogen, the oxygen, the phosphorus, the sulfur, they're all going to be involved in those macromolecules, but they're all going to be bonded together. So next thing we're going to discuss is bonding. And in this, I'm going to discuss ionic bonding. The first one I want to do is ionic bonding because it's going to help me explain ions. Now, in ionic bonding, you have ions that are going to be bonded together. An ion is an atom with a charge. Now, typically, atoms are neutral. Their protons equal their electrons. So if you go back to my carbon, it has 6 protons, 6 electrons. It's neutral. Even carbon-14, 6 protons, 6 electrons. It's neutral. but ions are not neutral, they're charged. And to explain ions in ionic bonding, I'm going to use sodium and chlorine. If you look on a periodic table, sodium has the atomic number of 11, which means it has 11 protons. And if it has 11 protons, it has 11 electrons. Chlorine has 17 protons and 17 electrons. And I got all that information from the periodic table. That's all, nothing made up. So if I were to actually try to draw a sodium atom, I'm going to start with the nucleus in the middle. And I'm going to draw the energy levels where the electrons are found. In the first energy level, you can fit a maximum of 2 electrons. So 2 down, 9 to go. In the second energy level, you can fit a maximum of 8 electrons. Does sodium have 8 to put there? Yes, it does. 1, 2, 3, 4, 5, 6, 7, 8. And then lastly, that 11th and final electron is on the outer shell, the third energy level in this case. This is called the valence electron. I'll define valence electrons for you in a moment after I do chlorine, okay? So with chlorine, you have the nucleus here, and let me use a different color because I'll need to. Chlorine has 17 electrons, so we'll put the first 2 on the first energy level, and that's it, it's maxed out. Then we'll have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons on the second energy level. And then 1, 2, 3, 4, 5, 6, 7. So for a total of 17. So on chlorine's outer energy level, it has 17 valence electrons, or excuse me, 7 valence electrons, and sodium has 1 valence. So I'm going to define what valence means. Valence electrons are the outermost electrons on an atom, or an ion for that matter. Not only are they the outermost, so in this case, sodium has 1 valence electron, and chlorine has 1, 2, 3, 4, 5, 6, 7. But they also dictate bonding. The valence electrons, even if you're doing covalent bonding, which we'll do momentarily, they are the ones that control bonding. But we have a problem. Unless you're a noble gas, every atom is unstable. To achieve stability, you have to have a complete valence shell. If you need to complete your first energy level, that means 2. Second energy level, 8. Third energy level would be 8. So right now, sodium is unstable. It has 1. It needs 8. Chlorine has 7. It needs 8. So both of these are unstable in their atomic form. And when I say atomic, I mean their atom form. So what happens is a concept called electronegativity. So in electronegativity, you have a periodic table. And on the periodic table, you find fluorine. Fluorine is located right about there. It's element number 9. Fluorine is the most electronegative element. Now, what does it mean to be electronegative? To be electronegative means the ability to attract electrons. And so we have to figure this out. Is sodium going to take chlorine's electrons? Because sodium needs 7 more. Chlorine has 7 on the valence shell. Or is chlorine going to take sodium's electron? Chlorine needs 1 more. Sodium has 1 there to give. So to figure out this problem, you have to ask yourself, which of the 2 elements that we're discussing here is closest to fluorine? Sodium is about right here in the periodic table, and chlorine is right below fluorine. So chlorine is closer to fluorine. So what this means is chlorine is more electronegative than sodium. So in this event, the valence electron in sodium is going to come over here and complete chlorine's outer shell. And that actually did sodium a favor. Sodium is now stable, but it's no longer a sodium atom. If you count it up, sodium still has 11 protons, but has 10 electrons now. So it has one more proton than electron, so it's going to be more positive by a factor of 1. It is now called a sodium ion. And in this case, it is a cation, which is a positively charged ion. Chlorine is going to no longer have 17 electrons. Chlorine has 17 protons and 18 electrons. So it is more negative by a factor of 1. So that symbol means it has a -1 charge. This is called an anion, and it's no longer called chlorine, it's called chloride. Negatively charged ions change the ending of their name from "ene," like chlorine to chloride, bromine to bromide, iodine to iodide, arsenic to arsenide, things like that. So that is how sodium, or that's how we get sodium ion and a chloride ion. Now they're going to be attracted by a concept known as electrostatic attraction. Electrostatic attraction simply means positive loves negative. And so they're going to be attracted to each other. So sodium and chloride, a sodium ion and a chloride ion makes sodium chloride. And they cancel each other out in a 1-to-1 ratio, because that's basically +1, that's -1, and +1 plus -1 is 0, so they're neutral. You now have an ionic compound, and they're held together by an ionic bond. And that's what you're going to see when we get to metabolism and the electron transport chain and maybe neurons, maybe the sodium potassium pump when we get to cells. But now we're going to transition to covalent bonding. Which is also known as molecular bonding. Okay. Covalent bonding is only in nonmetals, 2 or more nonmetals. And fortunately, schnapps are all nonmetals. So you're going to see mostly nonmetals when it comes to, or covalent bonding when it comes to this unit of biochemistry. So the example I'm going to give for you on this one is going to be H2O. In H2O, you have 2 hydrogen atoms and you have 1 oxygen atom. Now a hydrogen atom, oops, let me delete that. In a hydrogen atom, you have a nucleus and only 1 electron. Hydrogen's atomic number is 1. So it has 1 proton, which means it has 1 electron. So it looks like this. I'll go ahead and draw a second one. Remember that dot in the middle is the nucleus. Okay, and then over here, for oxygen, Oxygen has 6 protons and 6 electrons. Actually, no, excuse me. It has 8. I'm thinking of carbon. And so that's what an oxygen atom looks like. And if you notice, they're all unstable. Hydrogen each has 1 valence electron on the outermost shell. It needs 2. Oxygen has 6 electrons on the outermost shell. It needs 8. So in covalent bonding, you hear the word covalent. Co means like together. If you're going to cooperate, you're going to work together. If you if your parents are divorced and they're still helping to raise you, they kind of take you go to mom's house, you go to dad's house. They are co-parenting. So co means to work together, and the valent means the valence. So the valence electron is going to work together to achieve stability. That's what chemistry is almost all about, is the atoms on the periodic table, or the elements of the atoms on the periodic table, achieving stability. Right now, this is unstable. The hydrogens are unstable and the oxygens are unstable. So what we're going to do is I'm going to move this oxygen, and to try to clean this up a little bit, I'm going to draw what we call the Lewis structure. So there's hydrogen there. That 1 dot represents this 1 electron. That hydrogen represents that. That represents the hydrogen, the second one, and it's 1 electron. Then we have oxygen with 1, 2, 3, 4, 5, 6. So I'm going to move them over here. I'll plug that guy into there. Whoops, I kind of messed up my lasso. Let's try that again. Plug that in right there. Right there. And now this hydrogen is stable and now has 2 electrons thanks to the oxygen sharing. This hydrogen is stable and that oxygen is stable. So to give it all a nice clean look, that is what the molecular model for water looks like. This is H2O. These electrons here are unpaired. There's these guys right there. And they're there and there. You do have to draw them. So water is molecular. I know this because it is made up of 2 or more, but just in this case, just 2 nonmetals, hydrogen and oxygen. Now, the next thing I want to discuss is polarity. When I was in school, I could never understand what polarity actually means. It made no sense to me. So when you think about the Earth, Earth has a North Pole and a South Pole. Night and day are polar opposites. If you've ever heard of the bipolar disorder, it's a behavioral disorder where it seems like someone has 2 different moods. They can be happy and content, and then they could be angry and displeased. So it's like polar opposite emotions, bipolar. So polar generally means opposites. Well, when we talk about chemistry, charges are completely opposite. If a molecule or a bond is considered to be polar, this means that it possesses poles. And in this case, it has a positive end and a negative end. If you're hairy, you possess hair. If you're hungry, you possess hunger. If you're rich, you possess money. So if you're polar, you possess poles. You have a positive end and a negative end. Nonpolar simply means there are no poles. There are no positive and negative parts. Okay, now I'll get to what happens when you mix polar and nonpolar in a little bit, but to talk about water again, water is polar. Now, we know this because, again, when you look at the periodic table, fluorine is right there, oxygen is there, and hydrogen is here. Which one is closer to the ultimate electronegative negative element, fluorine? That would be oxygen. So oxygen is going to be a little bit more negative than hydrogen is. Now, these are not ions. So what we have here is oxygen is going to be a little more negative, but because it's not ionic, we're going to say it's partially negative. And this, the other end of this bond is going to be partially positive. Now I'll tell you what this little symbol is I'm using here. And then we're going to talk about this bond, partial negative, and then partial positive. This symbol is the lowercase letter delta. It kind of looks like an S, or if I were to actually draw it correctly, looks like a Reese's peanut butter cup, or not a Reese's peanut butter cup, a Hershey's Kiss. This means partial. Now, if I were you and I was sitting in this class, and I would be asking myself, how come he put 2 partial negative charges on oxygen and only 1 partial negative charge on hydrogen? Here's why. Because you're focusing on the bond. A bond like this has a negative end and a positive end. Partial negative, partial positive. Same thing here. Partial negative, partial positive. And so that's why oxygen has 2 of them and hydrogen only has 1. So water in this case is polar. Water is polar. It can mix with other polar substances, and it cannot mix with nonpolar substances. So now I'm going to transition into some of the special properties of water. Okay. Water is a very unique substance in the universe, and we know that on this planet you can't have water without life. The human body is about 70% water. Earth is 2/3 water, and it's because that we live in an area of the universe called the habitable zone, or our solar system is in the habitable zone, where we're just the perfect distance from our star, which is the sun, in which water can be liquid. If we were too close to the sun, water would be vapor. It would be all vaporized. If we were too far from the sun, water would be ice. It would be solid and you couldn't access it. We're in the perfect zone. So when astronomers at NASA are trying to find potential planets out in the universe that might actually be able to foster life, they look to see if those planets are in the perfect distance from their host star, their own version of the sun. Are they in that little Goldilocks zone? It's called the habitable zone or the Goldilocks zone. Are they just there so that water can be liquid? And that's definitely what allows there to be life on this planet. So to go back, let me bring a water molecule here. Oops. I'll just draw a new one. Okay. This bond right here, as we already mentioned, is a covalent bond, but it's also an intramolecular force. Intra means within. So this is a bond that is within the molecule. So it is an intramolecular force. But if I were to have another water molecule and another and another, we're going to talk about how they bond. Now, all those oxygens are going to be partially negatively charged, and those hydrogens are going to be partial positive. According to electrostatic attraction, positive likes negative. So if we were to actually have bonding, the hydrogen from this molecule will be attracted to the oxygen of that one. And same here. And I could go on and on and on forever. When water is in the liquid or solid state, it forms these bonds. Now, these bonds are connecting one molecule to another molecule. These are known as intermolecular forces. Inter means like between individuals. When you fly from the United States to Italy, you're going from one individual nation to another individual nation. That's called an international flight. But if you were to stay within the United States, like flying from Tampa to San Francisco, that would be an intra-national flight. And to be more specific, this type of bond is known as a hydrogen bond. Hydrogen bonding is one of the key reasons why water is so unique and able to support life. Hydrogen bonds are generally a bond that forms between hydrogen and oxygen, or hydrogen and fluorine, or hydrogen and nitrogen. In this case, it's between hydrogen and oxygen. These bonds can absorb a tremendous amount of heat without breaking. In fact, liquid water has hydrogen bonds, and it can absorb heat up to 100 degrees Celsius or 212 Fahrenheit, the same temperature. This is when at sea level, liquid water will vaporize into steam or just vapor because it's getting pretty hot. When that happens, the hydrogen bonds break. So just imagine that right now I'm boiling this water and it's getting so hot that the bonds are finally basically tapping out. They can no longer sustain themselves with the amount of heat that's being released towards them, so the bonds break. And now they're no longer bound to each other, so they're going to be able to vaporize and become a gas. Water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. At that temperature, the bonds become very strong to where the molecules cannot no longer move past each other, and they're going to become a solid. Okay? But hydrogen bonding is very important to understand that this is what absorbs the heat. And I'll go back to a little bit about hydrogen bonding in a little bit. But because of hydrogen bonding, you're able to actually have polarity, and that's just from the positive and negative. So remember that water is polar. And that simply means it possesses poles. There's a positive end, which are the hydrogens, and there's a negative end, which is the oxygens. Now, the fact that water is polar, you get to a constant of hydrophobic and hydrophilic. Water is called the universal solvent. Anything that's polar, water can generally break down. It can't break down everything because not everything is polar. But most polar substances can be broken down by water. Non-polar substances like oil and wax cannot. So if something is hydrophilic, hydro means water, philic means loving or liking, it can mix with water, which means that something would be polar. And then you could have hydrophobic, which would be like oil or wax. It cannot mix with water. And if it cannot mix with water, that means that it is nonpolar. And once again, that would be like oil or wax. And it could be motor oil, it could be soybean oil, canola oil, anything that's defined as an oil, or even waxes. All right. Now, let's talk about adhesion and cohesion. Because most of this planet is water-based, water has the ability to stick to itself or to stick to other surfaces. Water is considered sticky. It's mainly because of the hydrogen. And because of its polarity, water can bond with other water molecules. You know, this is how we form puddles or beating water off of a leaf or on your car. And then that would be cohesion. Then adhesion is where water can actually bond with other polar surfaces. So with adhesion, water bonds with any polar substance, a leaf, the ground, your skin. And then cohesion is just water bonding with other water. You know, because of adhesive and cohesive properties as well as capillary action, we're able to circulate blood throughout our body. Blood is mostly water. If you've ever stood up before and everything just goes black, you don't lose consciousness, but you kind of wait for your vision to catch up to you, you're dehydrated. That's called postural hypotension. Hypo means not enough. Tension means pressure. You don't have enough water in your system for the pressure to be strong enough to circulate effectively. You need to drink some water, you're dehydrated. So again, water is kind of sticky. It's able to stick to other polar surfaces. The density of water, this is very unique. Solid water is less dense than liquid. That is very weird. Imagine if you had a wheelbarrow full of golden bricks and you melted those golden bricks. So now you have like a pool of liquid gold. And then you actually got some more gold bricks and you threw the gold bricks into this gold pool. Would you expect those gold bricks to sink or float? I would imagine that you'd think that they would sink. But ice is less dense than water. They're both H2O. But solid water, ice, is less dense than liquid water. So when we have a lake, only the top is going to be ice. The bottom is still going to be liquid water. So on the bottom, you can have just the little fishies swimming around. And they're not going to have to worry about being frozen solid. Just the top level is going to be ice. If you've ever seen somebody fall through the ice, it's because it's liquid underneath. When we go by the laws of density, something that's less dense is going to float on top of something that is more dense. If something is more dense, it's going to sink. Liquid water is denser than solid water, so liquid water is going to go beneath solid water. Okay? And then finally for today, in this lesson, let's talk about water-specific heat and heat of evaporation. And this is all due to the hydrogen bonds. Water has a very high specific heat. I think it's like 4.184 joules per gram per degree Celsius. I might have those flip-flopped. What this means as far as specific heat is concerned is the amount of energy needed to increase the temp of 1 gram of a substance by 1 degree Celsius. And when it comes to water, it takes a lot of heat to actually get water to change. And I have an example for you. Let's say that you're at the beach. And you could either stand on the sand or the water. They're both underneath the same sun. But which one is going to be hotter? Typically, the sand is going to be hotter. The sand does not have hydrogen bonds. It is not able to absorb that heat without changing. So it has a very low specific heat. So it just absorbs a little bit of sunlight, or actually not light, but radiation, and its temperature is going to change drastically. So when you are barefoot in the sand, at least at the surface of the sand, exposed to the sun, it's going to be burning hot. But the water is not burning hot because it is absorbing that heat. And it's going to feel actually pretty good. Now, for those of you who like to walk your dog during the summer, you see this all the time around here in the Riverwalk downtown or in Bayshore Boulevard. People walk their dogs on the asphalt streets or on the concrete sidewalks. Asphalt and concrete have very low specific heats, which means that their temperatures will change drastically just with a little bit of solar radiation. So dogs actually can hurt their feet pretty badly and burn their paws if the owners aren't careful, because those surfaces are going to be very hot. But the grass, which is mostly water, is not going to be as hot. Now, not only does this have to do with why is this important as far as specific heat? Well, we're animals. And maybe not in Florida, where the temperatures can range from 20 degrees, maybe it might be 75 degrees in the morning, all the way up to maybe 95 degrees in the mid-afternoon. That's not a big change. But there's other places on Earth where the temperatures can fluctuate like 60 to 80 degrees. So if the environment is fluctuating so drastically, what does that do to life? Well, all life is mostly water-based. So if we have some sort of little bacterium, a little microscopic organism, and it's an environment where the lows are maybe 10 degrees Celsius and the highs are 30 degrees Celsius. That is a tremendous temperature swing, but its internal temperature is likely not going to be as drastically affected because it is water-based. So the great thing about us and having water with a high specific heat is that life doesn't fluctuate its internal temperature as dramatically as the environment. You know, when I go to the gym, I could be riding my bike to the gym or jogging to the gym, and it is hot as heck outside. I'm sweating. I feel like I'm going to pass out. They check my temperature now with all the precautions for COVID. I'm 97, 98 degrees. I feel like I'm overheated. I'm going to pass out. I'm fine, because all that heat that I'm exposed to outside, it's really not going to change, because it takes a tremendous amount of heat to actually break water. Or to change water, I should say, change water's temperature. Now, it can happen. You can manipulate water's temperature. You just have to have a tremendous amount of heat to do it. And then heat of vaporization is just the amount of heat it takes to get water to become a vapor. And water has a very high vaporization. So this is what makes it so remarkable for life and life on this planet. So that whenever we're trying to find life in the distant universe, we want to see if there's a planet out there that has the potential to have liquid water, because we know, according to the rules of life on this planet, liquid water is where it's at. Okay? That is going to do it for this lesson on basic chemistry and water. And I'm going to sign off now.